Welcome back to Chapter 18, Part 2, Two Sample Problems, where we're looking at samples that are independent. Well, as stated earlier, we're going to look and do a little bit of a review. So we're going to talk about statistics and parameters. Statistics, they come from a sample, and the parameter defines a population. We use statistics to estimate parameters. So in looking at this chart, we're going to look at some statistics that estimate parameters. So the first thing is we want to look at the mean. The sample mean, which is denoted by X with a bar over it, estimates mu, that funny looking U called mu, which is the population mean. Looking at standard deviation, our statistic is S. The sample standard deviation, it estimates sigma, the population standard deviation. And proportion, our statistic is denoted by a p hat. That's our sample proportion, and it estimates the population proportion, which is denoted by a p. Now we use statistics to make our confidence intervals. So our confidence intervals are about a population parameter, but we need to use a statistic in order to build them. And the basic form for a confidence interval is a statistic plus or minus a margin of error. And remember what the margin of error is. It's the critical value times the standard error of the sampling distribution of the sample mean in the case that we've been using in our class. Because our confidence intervals have been about the population mean. Now there are conditions that must be met in order to do confidence intervals in the way that we've done them in our class. And remember what they were. First of all, our samples had to come from a simple random sample. We had normality. And then the third one, that's what caused us the 4 different cases that we've learned in doing our confidence intervals. So let's look at them. Now in the first case, we had a one sample problem when our population standard deviation was known. The way in which we constructed the confidence interval is we had a sample of a certain size. That brought us into a sampling distribution of the sample mean, which gave us a standard error of sigma divided by the square root of n. So the way we constructed our confidence interval was the mean plus or minus our critical value times the standard error. Now the critical value we could find by knowing the confidence level, and we'd go to our table A and we'd find the critical value that goes with that particular confidence level. And we learned the 3 major confidence levels: the 90, which was 1.645, the 95, which the critical value was 1.96, and the 99% confidence interval, which if you go to table A is 2.575. But if you were more accurate and look at table C, when they show us the critical values, for a 99% confidence interval, you would say 2.576. So we learned those critical values. Now the standard error we would calculate ourselves by taking the population standard deviation that would be given to us in the problem divided by the square root of the sample size. Now 3b, remember the first 2 have been met, simple random sample and normality. 3b is what happens when sigma is unknown. Well, we now have to estimate sigma with the sample standard deviation, which is denoted by S. That we could no longer go to table A, but we had to go to table C, because we had to go to the t distributions to find our critical value. And now we need 2 pieces of information to find our critical value. We not only need to know our confidence level, but we need to know what's called degrees of freedom. And remember what degrees of freedom are. They're just n minus 1. So we needed both pieces of information in order to use table C to find our critical value. And the standard error for this particular distribution changed because we're in the t distributions, so the standard error is S divided by the square root of n. Now that was the first part of Chapter 17 when we were dealing with a one sample problem. At the end of 17, we started looking at 2 sample problems, and we talked about the 2 sample problems where the samples were dependent. Now in the 2 sample problem where we have dependent samples, the way we made our confidence interval is we had x bar plus or minus the critical value, t alpha over 2 degrees of freedom. In other words, we need to know both the confidence level and the degrees of freedom to get our critical value, times the standard error, which was s over the square root of n. But to take note here, what is x bar? X bar is the mean of the differences of the two samples. And s is the sample standard deviation of those differences. So this is when we had a two-sample dependent case, and that's how we'd make our confidence interval. Then we went to Chapter 18, and that's where we're working on now, where we're looking at a two-sample problem, but the samples are independent. One sample does not depend on the other. We're not looking for a before and after or something to that effect. We simply take the mean of one group and the mean of another and look at the means of those two groups. So the one sample doesn't depend on the other one in its formation. Now when we look at this one, we get the way that we make our confidence intervals. We actually look, our statistic is no longer just a singular number, but we have to do a x1 bar minus x2 bar. It becomes a singular number after you do the subtraction, but you have to subtract those two sample means from each other, and that's our statistic. And our critical value is still, we're at the student t distribution, table C, and we still need two separate pieces of information in order to find the critical value, the confidence level and the degrees of freedom. But in this problem, to get the degrees of freedom is a little bit different because you could have samples of different sizes. So we said that one way that we're going to do it is use the conservative method, and the conservative method is this. So for the degrees of freedom, we take the minimum of the smaller, we take the minimum of n1 minus 1 or n2 minus 1. Or another way to look at this is look at your two samples, find the one with the smallest sample size, subtract 1 from it, and that's your degrees of freedom. That's the conservative method. We're going to multiply that by the standard error for our two-sample independent problem, which remember from before we said that was a square root of this sum, s1 squared over n1 plus s2 squared over n2. Now let's take a look at tests of significance. So we talk about a test statistic when we do these hypothesis tests or tests of significance. And remember what the test statistic is. It's how many standard deviations your sample mean is in the null hypothesis distribution. So our basic form for the test statistic is we standardize our sample mean. And remember, to standardize was just x minus mu over sigma. In other words, whatever you got from your sample minus the population mean divided by the population standard deviation. But when we talk about population here, it's not, we're talking about the null hypothesis population. So we look at the value of our null hypothesis, its mean, and its standard deviation, which is a standard error. So let's look when we have a one sample where sigma is known. With that problem, we got our test statistic. Z0 is how I write it, so that it denotes that that's how many standard deviations it is in the null hypothesis distribution, and I'm looking at table A, the standard normal table, and so the test statistic is x bar minus mu naught divided by sigma over the square root of n, and I ought to put mu naughts in there. Now let's look at the case that we saw at the very beginning of Chapter 17. It was a one sample problem, but this time sigma was unknown. We didn't know the population standard deviation. Therefore, we had to estimate sigma with s. That brought us using the table C, the t distributions. And our test statistic now looks like t naught because we're going to those table C to the t distributions. And it's x bar minus mu naught divided by s over the square root of n, because all we have is the sample standard deviation. Now at the end of Chapter 17, we got into two sample problems, two sample dependent. But what happened with the two sample dependent, remember, is that it basically became a one sample problem because we took the two samples, subtracted them from one another, each like person 1 from person 1 of the other sample. We got those differences, and we were taking the means and standard deviations of those differences. So our test statistic looks just like the one above it. But it's x bar minus mu naught over s divided by the square root of n. But x bar is the mean of the differences, and s is the sample standard deviation of those differences. And when in Stat 250, we're always going to have in the null hypothesis that the means are equal to 0. So we can simplify our test statistic. In other words, we can get rid of minus mu naught, because we're always in Stat 250 going to say that mu naught equals 0. But in upper level stats courses, that's not always the case, and in real life, definitely not always the case. But in our class, for two sample problems, the mu naught value will always be 0.